At some point in the not-too-distant future, a small group of human beings will stand on the surface of another planet and look up at the sky. Earth will be visible. A pale point of light, smaller than a star, appears from here. Everything they have ever known, everyone they have ever loved, reduced to something you could cover with your fingernail. And if they tried to call home in that moment, the signal would take anywhere from 3 to 24 minutes to arrive, depending on where the two planets happen to be in their orbits. There is no real-time conversation at that distance, no immediate response. If something goes wrong, the answer to a question asked in a moment of crisis arrives long after that moment has passed. For the first time in the history of human exploration, there is no way back that does not require waiting. The orbital mechanics that govern a return journey only align once every 26 months. Miss that window for any reason, and the crew stays. And some of the people planning these missions have already begun to ask a question that most of us are not ready to sit with. Not whether the mission could fail, but whether it could succeed, exactly as planned, and the people who go simply never come home. What does that distance do to a human being, not just physically, but in ways that cannot be measured by any instrument? What happens to a person when the world they came from becomes unreachable? And what does it mean to volunteer for something that the people sending you there are not certain you will survive? The question is no longer whether we can reach Mars. It is what we are actually asking of the people who go. If you're settling in for the night with this one, take a second to like the video. It's a small thing, but it helps more people find their way here. Now, let's begin. We begin not with distance, but with resemblance. Mars does not feel like a stranger at first glance. It feels incomplete. A horizon that almost belongs to us, a sky that behaves almost correctly, a day that moves with a rhythm your body would recognize, lasting 24 hours and 37 minutes, close enough that early mission planners quietly chose to follow it instead of resisting it. Time there does not fight you, it lulls you into familiarity. The surface continues that illusion. You would see seasons shifting across the planet, thin frost gathering at the poles, dust lifting into weather systems that move with intent. Valleys stretch for thousands of kilometers, carved by forces that once resembled rivers. There is a canyon system so vast it could span from New York to Los Angeles without interruption. At a distance, nothing feels impossible. It feels abandoned. But that familiarity hides a missing foundation. Mars is what Earth becomes when its internal engine fails. 4 billion years ago, this world held a thick atmosphere and stable liquid oceans. Not speculation, but evidence written into its crust. Magnetized rocks preserve the memory of a once active magnetic field, meaning molten metal moved deep inside, generating protection. Mineral deposits form only in standing water, confirming long-vanished seas. Shoreline patterns trace the edges of basins that no longer hold anything. The failure began deep below the surface. Mars is smaller than Earth, and that difference shapes everything that followed. A smaller planet loses heat faster. Its iron core cooled more quickly, and as it cooled, it slowed. When motion inside that core stopped, the magnetic dynamo ceased. A dynamo is simply the process of moving conductive fluid, generating a magnetic field. Without it, Mars lost its shield. From that moment, the solar wind had access. This constant stream of charged particles from the sun began stripping the atmosphere away, atom by atom, not violently, but relentlessly. Over hundreds of millions of years, the pressure dropped, the air thinned, water could no longer remain stable on the surface. It either escaped into space or retreated underground as ice. What remained was a shell of a planet, still shaped like Earth, but no longer functioning like it. And this is the environment waiting for us. Not ancient history, but present condition. Every hazard we will encounter traces back to that single collapse. The missing magnetic field, the thin air, the cold surface, all consequences of a system that could not sustain itself. Mars did not transform into something alien, it simply stopped protecting itself. So when we imagine standing there, looking across that quiet landscape, we are not visiting a different kind of world. We are stepping into a version of our own that failed to continue. And the question that settles in slowly is not how we survive Mars, but whether survival is even meant to happen in a place where the planet itself could not endure. You do not choose the moment you leave, and you do not choose the moment you return. The decision feels human, but it is not yours. It belongs to motion already in progress. Long before any spacecraft exists, Earth and Mars are moving through their own paths around the Sun, each following a schedule that cannot pause or adjust. We step into that motion, or we wait. Earth completes one orbit in 365 days. Mars takes 687. That difference means their positions are always shifting, sometimes drawing closer, sometimes drifting far apart across hundreds of millions of kilometers. Most of the time, they are simply not in the right place. The distance is wrong, the angles are wrong, the energy required becomes too large to overcome. But there is a narrow pattern hidden in that motion. Every 26 months, the geometry aligns just enough to allow a specific path between them. This path is called a Human transfer orbit, which means the most efficient curve that lets a spacecraft leave one orbit and meet another using the least possible energy. It is not a straight line, it is a calculated arc, shaped by gravity and velocity already in motion. To use it, everything must happen at the right time. Launch too early or too late, even by a few weeks, and the fuel required increases beyond what any current or near future system can carry. The opportunity does not stretch to meet you, it closes. Once you commit, the journey itself unfolds at a fixed pace. The transit takes between 6 and 9 months, depending on how favorable that particular alignment is. Some windows shorten the distance slightly, others extend it, but none allow urgency. You travel as the physics permits, not as the situation demands. Arrival does not restore flexibility. After landing, the same alignment constraint appears again, now governing the return. You must wait for Mars and Earth to move back into position. That wait lasts between 14 and 20 months. During that time, leaving is not an option. The path home does not exist yet. This creates a mission timeline that cannot compress. The shortest round trip stretches to roughly 30 months, often closer to 36. No emergency changes that. No system overrides it. The planets do not respond to need. And this is where the trap becomes real. Imagine a serious medical condition developing 8 months into that surface stay. The next return window may still be 12 months away. Treatment must happen there, with whatever resources exist, because departure is mathematically impossible. We often imagine better technology, solving distance, faster engines, stronger materials, more powerful rockets. But this constraint sits deeper than engineering. It is written into orbital mechanics, the basic laws that govern how objects move through space. A perfect spacecraft would still wait. So the mission is never just about reaching Mars. It is about accepting a schedule set by celestial motion, where departure and return are brief openings in a system that otherwise remains closed. A hatch closes and the world reduces to volume. Inside, space is measured not in distance, but in cubic meters. Current Mars transit designs allow roughly 100 to 300 cubic meters of pressurized interior for a crew of 4 to 6, a space comparable to a modest two-bedroom apartment, but shared continuously, without doors that lead outside, and without any change in environment for months. You move through the same pathways, touch the same surfaces, repeat the same motions until they become the structure of your day. The window offers less than expected. During normal operations, the spacecraft exterior is illuminated by reflected sunlight, and that brightness overwhelms the faint light of distant stars. The sky beyond appears as a flat black field, empty to the eye. You look out, and there is nothing to orient yourself against. No horizon, no movement, only the knowledge that motion continues. But inside, motion is controlled and scheduled. Each day begins with exercise, not optional, lasting 2 hours to slow the loss of muscle and bone that begins immediately in microgravity. Microgravity means near weightlessness, where objects do not press against surfaces and the body no longer experiences load. Without that load, tissue begins to weaken. Exercise becomes maintenance, not improvement. After that, the schedule fills with system checks, scientific tasks, and structured psychological evaluations designed to monitor stress and cohesion. Food arrives in sealed packets, engineered for caloric density and long-term stability. Taste becomes less about preference and more about compliance. Variety is preserved carefully because studies show that repetition reduces appetite and reduced intake leads to weight loss and declining immune function. Eating is both nourishment and management. Sound becomes constant. Ventilation systems move air. Pumps circulate fluids. Life support systems regulate pressure and composition. Together, they produce a continuous mechanical hum that never fully disappears. Over time, this low-level noise alters sleep patterns and elevates stress hormones, even when the crew no longer consciously notices it. Water follows a closed loop. Urine is collected, purified, and returned as drinking water through systems already proven aboard the International Space Station. The process is efficient and necessary. Acceptance becomes routine. The air itself develops a signature. In a sealed environment, human presence accumulates. Odors from bodies, food, and equipment blend with recycled air into something metallic, slightly sour, and persistent. It does not leave. It becomes part of the habitat. Sleep separates from natural cycles. Without external light cues, circadian rhythm drifts. The circadian rhythm is the internal clock that regulates sleep and wake patterns over approximately 24 hours. Here, it requires intervention. Crews use controlled lighting and medication to maintain alignment, managing rest as a system rather than an instinct. And across 9 months, repetition becomes the defining condition. Each day resembles the last, structured by necessity and bounded by walls that do not move. But outside, distance continues to grow, steadily and without interruption, carrying you further from the only environment your body has ever known. Before anything touches the body, something already passes through it. You do not feel it. You do not hear it. It leaves no immediate trace, but it is there, moving constantly through the structure of the spacecraft and through you with equal indifference. Radiation in deep space is not an event, it is a condition. On Earth, we live beneath a shield that rarely enters awareness. The planet's magnetic field deflects charged particles arriving from the sun and from far beyond the solar system, bending their paths away before they reach the surface. The moment a spacecraft leaves low Earth orbit, that protection ends. Nothing replaces it. The environment changes completely, even though nothing visible announces the shift. But not all radiation behaves the same way. There are 2 primary sources, and each presents a different problem. The first is galactic cosmic rays, often shortened to GCRs. These are high-energy particles created by distant supernova explosions, traveling at a significant fraction of the speed of light. They do not arrive in bursts. They arrive continuously. When they encounter the spacecraft, they pass through metal, plastic, and human tissue with minimal resistance. Current materials cannot fully stop them. They simply continue. The second source is solar energetic particles, known as SEPSI. These come from the sun during solar flares and coronal mass ejections, which are sudden releases of energy and charged particles into space. Unlike GCRs, these events are episodic but intense. During a major event, radiation levels can rise to dangerous levels within hours. The crew responds by moving into a dedicated shelter, a small compartment surrounded by additional shielding, where they may remain for days until the flux decreases. Measurements taken during previous missions provide a baseline. During the 2011 to 2012 transit of the Mars Science Laboratory, instruments recorded an average exposure of 1.8 millisieverts per day. A millisievert is a unit used to measure the biological effect of radiation on the human body. Over the course of a typical round trip, this accumulates to approximately 600 millisieverts, which matches the current career exposure limit set by NASA for astronauts. That limit is reached before any surface operations begin. Inside the body, the interaction is precise and ongoing. GCRs carry enough energy to sever strands of DNA, altering the instructions that cells rely on to function. They damage the myelin sheath, the protective layer around nerve fibers that allows electrical signals to travel efficiently. They also generate oxidative stress, which means chemical reactions that degrade tissue within the central nervous system. In 2019, experiments at the NASA Space Radiation Laboratory exposed mice to radiation levels comparable to a Mars mission. The results showed measurable memory loss, reduced cognitive flexibility, and increased anxiety-related behavior. These changes did not reverse after exposure ended. But there is no complete pharmaceutical protection. Research continues, but no medication currently exists that can shield the brain from this type of damage in a flight-ready form. The crew carries mitigation strategies, not solutions, and this exposure does not mark the peak. It is only the beginning of what the journey imposes. At some point, your body stops resisting the absence beneath you. It does not panic, it recalculates. For millions of years, human physiology developed under a constant pull, a steady downward force shaping bone, muscle, and circulation. Remove that force, and the body does not recognize it as danger. It interprets it as excess. Microgravity, meaning near weightlessness, signals that structural support is no longer required. The body begins conserving energy by reducing what it no longer needs. This process is not gradual in the way we expect. It is immediate and systematic. Bone is the first to change in measurable ways. Weight-bearing regions, especially in the spine and legs, begin losing density at a rate of approximately 1 to 2% per month. This loss is uneven, concentrating in areas once responsible for supporting posture and movement. On Earth, the most aggressive osteoporosis, a condition where bones weaken over time, progresses far more slowly. Here, the rate accelerates to nearly 10 times that speed. Muscle follows closely behind. Without resistance from gravity, postural muscles and those used for walking begin to atrophy, which means they shrink due to lack of use. Within the first 2 weeks, up to 20% of lower body muscle mass can diminish if no countermeasures are applied. Movement continues, but it no longer requires strength in the same way. But the changes extend beyond structure. Fluids within the body shift upward. Without gravity pulling them toward the lower body, approximately 2 liters redistribute toward the chest and head. This creates a persistent sensation similar to nasal congestion, as if you are always slightly unwell. The increased pressure inside the skull alters normal function. That pressure reaches the eyes. Around 40% of astronauts on long-duration missions develop visual changes linked to this shift. The optic nerve, which transmits visual information to the brain, becomes compressed. The shape of the eyeball itself can flatten slightly. In some cases, vision does not fully return to its previous state after coming back to Earth. The heart adjusts as well. In a weightless environment, it no longer works against gravity to circulate blood. Over time, it reduces its muscle mass and pumping capacity, becoming more efficient for this new condition. But this efficiency does not translate back easily. Astronauts returning from extended missions have experienced irregular heart rhythms as the body readjusts. The immune system also begins to behave differently. Studies from the International Space Station show that dormant viruses within the body can reactivate. These include herpes simplex and varicella zoster, which remain inactive under normal conditions. In microgravity, immune surveillance weakens, allowing these viruses to emerge again. But none of this happens unchecked. Daily exercise, lasting 2 hours, is designed to slow these processes. Resistance machines simulate load. Cardiovascular systems maintain circulation. Yet these interventions only reduce the rate of change. They do not prevent it. Across 9 months, the body adapts to a new baseline. Not stronger, not more capable, but recalibrated for a different environment. And when the journey ends, what arrives is no longer the same system that left, but one already altered, carrying forward into conditions that introduce an entirely new set of demands. There is a point where falling becomes the only option. After months in transit, the spacecraft meets Mars not gently, but at speed, entering the upper atmosphere at roughly 19,000 kilometers per hour. At that moment, every system shifts from preservation to survival. Engineers have named this phase the 7 minutes of terror, not as drama, but as description. The spacecraft must lose nearly all of that velocity in less than 7 minutes. It cannot slow gradually over hours. It must do so quickly, using only what it carries and what Mars provides. The first tool is atmospheric drag, which means resistance from air molecules colliding with the vehicle as it descends. But Mars offers very little. Its atmosphere is about 1% the density of Earth's, thin enough to limit braking, yet thick enough to create extreme heat. As the vehicle plunges downward, friction raises temperatures on the heat shield to around 1,600 degrees Celsius. The shield is built from ablative material, which means it is designed to burn away in a controlled manner, carrying heat with it as layers are lost. This process must remain precise. A difference of millimeters in thickness determines whether the underlying structure remains intact or fails. But communication offers no assistance here. Signals between Mars and Earth take minutes to travel. By the time data reaches mission control, the landing has already finished. No correction arrives in time. Everything unfolds autonomously, guided by onboard systems and preloaded sequences. As velocity decreases, parachutes deploy, but only briefly. The thin atmosphere cannot support them for long. The spacecraft continues descending, transitioning to powered flight. Retro rockets ignite, firing in a sequence that must align perfectly with altitude and speed. Too early, and fuel is wasted before landing. Too late, and there is no recovery. The margin for error is measured in seconds. We have seen this process before, in part. In 2021, The Perseverance rover transmitted the first detailed footage of Mars' entry, descent, and landing. Cameras captured the supersonic parachute opening against the thin sky, the heat shield separating and falling away, and the sky crane lowering the rover gently onto the surface. It appeared controlled, almost routine, but Perseverance weighed just over 1 ton. A human mission requires landing between 20 and 40 tons. The physics does not scale cleanly. Heavier mass carries more momentum, demanding greater force to slow it, while the atmosphere remains unchanged. No mission has yet demonstrated this capability. The problem remains open. And so, the final moments depend on systems that have never operated at the required scale. When the descent ends, dust rises around the landing site, obscuring the view. The engines cut. Motion stops. Inside, the crew arrives not as they left, but altered by the journey. They step into an environment that offers no tolerance for failure, where every layer between them and the outside defines survival. And somewhere nearby, waiting or not, is the single path that determines whether this arrival is temporary or permanent. Long before anyone steps onto Mars, something else must arrive first. Not a habitat, not supplies, a promise. The vehicle that will carry them home has to be waiting, silent and complete, before departure from Earth even begins. Without it, the mission changes meaning entirely. But sending that vehicle ready to launch is not practical. The mass alone prevents it. A rocket capable of lifting a crew from the Martian surface into a return trajectory requires hundreds of tons of fuel. Transporting that fuel from Earth would demand launch capacity far beyond anything currently operational or realistically planned. The cost scales beyond feasibility. The physics resists it. So the design shifts from delivery to creation. Instead of bringing fuel, the mission must produce it on Mars. This approach is called in situ resource utilization, often shortened to ISRU. It means using materials already present on another world to generate what is needed for survival and return. The idea is elegant. The execution is not. The primary method proposed is the Sabatier reaction, a chemical process discovered in the early 20th century. It combines carbon dioxide, which is abundant in the Martian atmosphere, with hydrogen to produce methane and water. Methane becomes rocket fuel. The water is then split through electrolysis, which is the use of electricity to separate molecules into oxygen and hydrogen. The oxygen supports both combustion and life support. The hydrogen cycles back into the process. But hydrogen presents a problem. Mars does not offer it freely in accessible form. It must either be transported from Earth, where it is difficult to store due to its tendency to escape containment, or extracted from subsurface ice, which requires locating deposits, drilling, and processing under conditions never tested at scale. Each option introduces risk. Time adds another constraint. Current demonstrations suggest that producing enough fuel for a Mars ascent vehicle would take approximately 16 months under ideal conditions. This means the return system must be deployed in advance, landing on Mars and beginning fuel production well before the crew departs Earth. When the crew arrives, the vehicle must already be prepared. But what if it is not? If the process falls short, if a system fails, or if production slows below required levels, there is no alternative waiting. The next opportunity to send assistance aligns with the same orbital constraints that govern departure. Roughly 26 months later, the timeline does not adjust. We have taken small steps toward this capability. The MOXIE experiment aboard the Perseverance rover demonstrated the extraction of oxygen from Martian carbon dioxide, producing about 6 grams per hour during its operation. It proved the concept works. But scaling that output to mission-level requirements demands a system roughly 200 times more powerful, operating continuously, and doing so reliably in an environment where repair options are limited. So the return vehicle becomes more than equipment. It becomes a dependency that must function perfectly for years before it is ever used. It must survive launch, landing, environmental exposure, and continuous operation without failure. But beneath the engineering, the implication remains steady. The path home exists only if this system succeeds, and every calculation leading to that moment assumes that it will. The first step onto Mars is not a beginning, it is an exposure. Every system you rely on is now external, carried with you, separating you from conditions that cannot be negotiated. The surface does not present one danger at a time. It layers them, each one amplifying the next. The atmosphere defines everything immediately. Surface pressure averages around 0.6% of Earth's sea level, comparable to standing at 35,000 meters above Earth, far beyond where unprotected humans can survive. There is not enough pressure to keep liquid water stable inside the body. Without a pressurized suit, bodily fluids begin to boil at normal body temperature. Survival depends entirely on what surrounds you. Temperature adds another constraint. The average surface temperature sits near -60 degrees Celsius, but it does not remain stable. Near the equator, in direct sunlight, temperatures can briefly rise to around 20 degrees. In polar regions, they fall to -125. The variation is not gradual. It shifts with location and time. A failure in thermal control, even momentary, can become critical within minutes. But the ground itself introduces a quieter threat. Martian soil, known as regolith, contains perchlorates at concentrations between 0.5 and 1% by mass. These are chemically reactive compounds that disrupt thyroid function and increase cancer risk with prolonged exposure. Dust becomes the carrier. Once it enters a habitat, it remains unless actively removed. And this dust is not passive. Individual particles average about 1.5 microns in diameter, small enough to penetrate deep into lung tissue. They carry an electrostatic charge, causing them to cling to surfaces, including suits, equipment, and air filters. Unlike Earth's dust, shaped by water erosion into smooth grains, Martian particles are angular and sharp. When inhaled, they do not settle gently. They cut. Above the surface, radiation continues without interruption. Measurements taken by the Curiosity rover indicate an average exposure of 0.67 millisieverts per day. That is roughly equivalent to receiving a full-body CT scan every 5 to 6 days, continuously, without pause. Over time, the cumulative effect becomes significant, adding to the exposure already received during transit. But the environment does not remain static. Mars produces dust storms that exceed anything observed on Earth. In 2018, a storm expanded from a regional event to a global system lasting 98 days. It reduced incoming sunlight by more than 99% and disabled the Opportunity rover by depriving it of power. For a human crew, such a storm affects visibility, energy production, and external operations simultaneously. This creates a constraint that has no clean solution. To reduce radiation exposure, you move underground, using regolith as shielding, but extended confinement introduces its own psychological strain. To counter that, you go outside. Each excursion exposes the suit to abrasion, increases dust infiltration, and adds to cumulative radiation dose. The balance cannot be resolved, only managed. And above all of this, the sky remains present. During the day, it appears butterscotch pink, colored by fine dust scattering sunlight through the thin atmosphere. At sunset, the light shifts, and a blue glow forms around the sun, an inversion of what we see on Earth. It is precise, it is unfamiliar, and it remains constant, marking a place where every condition shapes what the human body can endure and how long it can continue to do so. Before a home exists, there is only a boundary. A thin shell separates interior from exterior, holding pressure against a world that offers none. The first structures delivered from Earth provide that boundary, but only briefly. Their size is constrained by launch mass, and that constraint limits how much space can ever arrive intact. What is delivered is not a settlement, it is a starting point. But long-term habitation requires more than what can be carried. It requires expansion, and expansion must come from what surrounds you. The accepted approach among mission planners is to build using Martian material itself, turning the surface into structure. This is in situ construction, meaning construction that uses local resources rather than imported ones. The idea reduces mass from Earth, but introduces methods that have never been proven at full scale. One approach uses additive manufacturing, often called three-dimensional printing, where layers of processed regolith are deposited to form solid walls. Laboratory tests have shown that Martian soil simulants can be shaped this way, but no system has operated under actual Martian conditions, where temperature swings, dust, and reduced gravity affect every stage of the process. Another method uses sulfur concrete. Mars contains abundant sulfur, and when heated, it becomes a binding agent that can replace water-based cement. This avoids the need for liquid water, which is scarce and difficult to manage. A third approach begins with inflatable modules. These are lightweight structures delivered compactly, then expanded and covered with regolith. The covering serves a critical purpose. Radiation on the surface remains high enough to prevent long-term exposure. To reduce it to levels comparable with the International Space Station, living areas must be buried beneath at least 2.5 meters of soil. The habitat becomes something you build downward, not upward. But there is a natural alternative. Mars contains lava tubes, which are large underground tunnels formed when flowing lava cooled on the outside while remaining molten within. When the flow drained, it left behind hollow passages. Because Mars has lower gravity, these structures can reach dimensions far beyond those on Earth. Some models suggest widths approaching 1 kilometer and lengths extending for hundreds of kilometers. In theory, these spaces could house entire communities, protected by natural rock overhead. Access remains uncertain. No mission has entered one. Locating stable entrances, reinforcing interior surfaces, and sealing them for pressurization all require techniques that have not been tested beyond concept studies. The scale is promising, but the path is unclear. Power determines whether any of this can function. Solar energy on Mars provides about 43% of what reaches Earth, and that value drops further as dust accumulates on panels. During large storms, sunlight can be reduced to near zero. Systems that depend solely on solar input become unreliable, so attention shifts to nuclear fission. This is a process where atoms split to release energy, producing steady power independent of sunlight. The kilopower reactor, developed by NASA, is a compact system designed for planetary surfaces, generating between 1 and 10 kilowatts. It represents the minimum threshold needed to sustain life support, construction, and basic operations. And within these constraints, the habitat takes form, not as a structure placed onto Mars, but as something shaped from it, enclosed beneath it, and powered against it. You step onto Mars and, for a moment, nothing feels dramatically wrong. You can stand, you can walk, you can move with a rhythm that resembles what your body remembers. Gravity is present, pulling you downward with about 38% of Earth's strength. It is enough to feel familiar, enough to feel manageable, and that is where the problem begins. Because this is not the absence of gravity, it is a replacement. Your body does not remain in transition. It adapts. Over time, it begins to treat this reduced pull as the new constant, the new normal, around which every system reorganizes itself. Bones, muscles, and circulation settle into an equilibrium designed specifically for this environment. In microgravity, the body loses structure in ways that have been studied extensively. Astronauts returning from the International Space Station, even after 6 months, undergo rehabilitation and gradually recover function under Earth's gravity. The body remembers what it was built for. It rebuilds, slowly, with effort. But Mars does not remove gravity. It alters it just enough to trigger a different response. At 38%, there is still load, still resistance, still a reason for the body to maintain structure. But that structure no longer needs to support Earth-level force. It becomes lighter, more efficient, calibrated precisely to what is required and nothing more. After 12 to 18 months, current research suggests that this recalibration may become deeply embedded. Returning to Earth would not feel like recovery. It would feel like overload. Every movement would carry more than double the weight the body has adapted to. Not occasionally, constantly. The joints would experience this first. Knees, hips, and the spine would absorb compressive forces they are no longer conditioned to handle. Cartilage and connective tissues, adjusted for lower stress, would face continuous strain. Injury becomes not a possibility, but an expectation built into the mechanics of movement. The cardiovascular system follows the same pattern. The heart, having adapted to pump blood in a lower gravity environment, reduces its workload over time. Its size and strength adjust accordingly. Returning to Earth would demand a sudden increase in output, similar to asking a system trained for rest to perform continuous exertion without preparation. We have seen partial versions of this. Astronauts returning from extended missions often require 6 to 12 months of rehabilitation to walk normally again. Some never fully regain their original bone density. And that occurs after exposure to microgravity, which represents a more extreme but temporary condition. But Mars introduces something less studied and potentially more permanent. A crew member spending 18 to 24 months on the surface would arrive back on Earth with a body that has not merely weakened, but redefined itself around a different gravitational constant. There is no clinical data for that transition, no established recovery path, no guarantee that full function can be restored. And so the question shifts quietly. It is no longer about whether a return vehicle can bring you back. It is about whether the body that returns would still belong in the place it left. A conversation begins, and the reply does not come back in time. You speak, you wait, and the silence stretches past expectation before any response returns. This delay is not a technical glitch. It is the structure of distance itself, shaping how connection works and how it slowly changes. The closest approximation we have studied took place on Earth. The Mars 500 experiment conducted by the European Space Agency and Russia's Institute of Biomedical Problems, sealed 6 volunteers inside a facility in Moscow for 520 days. The space measured about 550 cubic meters, designed to simulate every phase of a Mars mission, including transit, surface operations, and return. The participants lived without direct contact, following a schedule that mirrored what a real crew would experience. But the results did not emerge all at once. They appeared gradually, unevenly, in patterns that revealed how isolation reorganizes behavior. One crew member developed a persistent sleep disorder and became almost entirely inactive, reducing movement to minimal levels for extended periods. Another began sleeping between 12 and 14 hours each day, withdrawing from shared routines. The group divided, not through conflict at first, but through drift, separating into those who maintained engagement and those who retreated inward. That separation widened with time. Communication delay was built into the simulation. Messages carried a lag, preventing real-time conversation with anyone outside. Participants consistently rated this as one of the most difficult aspects of the mission. Without immediate feedback, dialogue changes. It becomes less spontaneous, less supportive, more deliberate, and more distant. But there is a deeper pattern that appears across isolated environments. It is known as third quarter syndrome, a psychological phase observed in Antarctic winter missions, submarine deployments, and extended space habitation. Around 3/4 of the way through a mission, motivation declines, mood shifts, and irritability increases. The assumption behind this pattern is that the end is approaching, that relief is visible. On a one-way journey, that structure does not apply. There is no final phase, leading back to familiar conditions. The timeline extends forward without a defined conclusion. The psychological framework that supports endurance has no reference point. Research in other extreme environments shows that isolation alters the brain itself. A 2021 study of Antarctic winter crews found measurable reductions in gray matter volume after 14 months, particularly in the hippocampus, a region associated with memory and spatial awareness. The change was physical, not abstract. But the external reality continues alongside these internal shifts. The crew will receive messages from Earth carrying news of events they cannot respond to directly. The loss of a parent, a friend, a partner will arrive through delayed communication without the presence of others who share that grief. The experience unfolds in isolation, and then the routine resumes. Within the habitat, relationships evolve under constant proximity. Conflict becomes inevitable, not as failure, but as a consequence of confinement and repetition. Every long-duration mission has documented it. The question is not whether tension appears, but whether it can be managed without breaking the structure that keeps everyone alive. A signal appears, then fades, leaving behind a question that does not settle. In 2003, ground-based telescopes detected methane in the atmosphere of Mars, a gas that should not remain there for long. Under ultraviolet radiation, methane breaks down in roughly 400 years, which means any detection implies a recent source. Something, somewhere, is replenishing it. At first, the measurement stood alone, but in 2013, the Curiosity rover began confirming methane at Gale Crater, providing data from the surface itself. What emerged was not a constant presence, but a pattern. Methane levels rose during the Martian summer, then declined again in winter, forming a seasonal cycle that does not align with any well-understood geological process. The pattern repeats, but its origin remains uncertain. But the signal is not stable. In June of 2019, Curiosity recorded a spike reaching 21 parts per billion, the highest concentration observed. Within days, it dropped back to previous levels. The gas appeared, intensified, and then dispersed without leaving a clear trace of how or why it changed so quickly. There are two broad explanations. The first is geological. Certain reactions between water and specific rock types can produce methane, a process known as serpentinization, where minerals transform under heat and pressure. Ancient organic material, if present, can also release methane when warmed. These mechanisms do not require life. They operate through chemistry and time. The second possibility is biological. On Earth, methane is often produced by methanogens, microorganisms that generate methane as part of their metabolism. If similar organisms exist on Mars, they would likely reside underground, protected from radiation and extreme surface conditions, possibly within briny liquid water. In this scenario, methane becomes a byproduct of life, continuing in isolation. But another layer complicates the picture. The ExoMars Trace Gas Orbiter, designed to detect atmospheric gases with high precision from orbit, has reported no methane presence. This contradicts the surface measurements. Two instruments, observing the same planet, provide results that do not align. The discrepancy has not been resolved. If the methane is biological, then Mars is not entirely inactive. Life would exist now, not as a relic, but as an ongoing process beneath the surface. The first human crew would not only arrive as explorers, but as the first capable of directly accessing and studying these environments. But their presence introduces a risk that cannot be fully controlled. Earth-based microorganisms are resilient. Bacillus cephensis, a species found on spacecraft components, survived sterilization procedures and was later detected on the exterior of the Curiosity rover. If similar organisms reach the Martian surface or subsurface, they could alter any native environment they encounter, and this creates a tension that remains unresolved. The search for life drives exploration, but the act of exploring may interfere with what is being sought. Any biological discovery must be interpreted through the possibility of contamination. The closer we get, the more uncertain the distinction becomes. The storm does not arrive as a wall. It begins as a lifting. Fine particles rise from the surface, carried by winds that seem ordinary at first, moving across open terrain without clear boundary. Then, something changes. The air warms unevenly, and the dust itself begins to drive the system forward. Mars produces storms larger than anything on Earth because of this feedback. The atmosphere is thin, so it heats quickly when sunlight reaches the surface. That uneven heating generates wind. The wind lifts dust. Once airborne, those particles absorb solar radiation, warming the surrounding air further. Warmer air moves faster, creating stronger winds, which lift more dust. The cycle reinforces itself, expanding outward until a local disturbance becomes something far larger. We have seen this before, long before any crew considered arrival. In 1971, the Mariner 9 mission reached Mars, only to find the entire planet obscured by a global dust storm. For months, the surface could not be seen. Mapping operations were delayed until the atmosphere cleared enough to reveal the terrain below. The storm did not pass quickly. It settled slowly, over time. But modern observation has shown how rapidly such events can grow. In late May of 2018, a regional storm formed in the northern hemisphere. By June 20th, it had expanded to encircle the entire planet. By July, it reached peak intensity. It did not fully dissipate until September, lasting 98 days. For that entire period, sunlight reaching the surface dropped to near zero in affected regions. The Opportunity rover experienced this directly. Its solar panels, normally producing around 645 watt-hours per day, fell to approximately 22. That is a reduction of about 96%. Without sufficient energy, its systems shut down. Communication ceased. It never recovered. But for a human crew, the consequences extend further. Solar power supports not just movement or communication, but life itself. Heating systems maintain temperature within the habitat. Oxygen is generated and circulated. Water is processed and recycled. Without consistent power, these processes fail in sequence. A storm lasting 3 months becomes a continuous constraint on survival. Outside, conditions deteriorate quickly. Visibility drops as dust thickens in the air, reducing contrast and obscuring landmarks. Particles accumulate on every exposed surface within minutes. They carry charge, cling to materials, and abrade seals and joints. Extravehicular activity becomes nearly impossible, not because of a single factor, but because multiple systems degrade at once. But predicting these storms remains uncertain. Current models cannot reliably determine where or when a regional event will expand into a global one. The crew may receive days of warning, or hours. The transition is not always gradual. Even after the storm subsides, its effects continue. In 2001, a global event left dust suspended in the upper atmosphere for more than a year. That material does not disappear. It circulates, settles slowly, and remains part of the air system the crew must manage. And within a sealed habitat, every particle that enters must be filtered, contained, and removed. The storm may pass outside, but its presence lingers, integrated into the environment in ways that cannot be ignored. A meal begins long before anything is cooked. It begins with mass, distance, and the cost of moving both. Every calorie that cannot be produced locally must be carried across interplanetary space, packaged, protected, and delivered months after it leaves Earth. Under current launch economics, placing cargo into Mars orbit costs tens of thousands of dollars per kilogram, with transit times measured in many months. Food becomes freight first, nutrition second. For a crew of 4, the requirement is steady and precise. Roughly 12,000 calories are needed each day to maintain basic function. Over a year, that becomes about 4.4 million calories, translating to approximately 550 kilograms of food at average caloric density. The numbers are manageable in isolation, but they repeat, year after year. But resupply does not scale easily. Even if future systems reduce launch costs to around $100 per kilogram, transporting 550 kilograms annually still demands continuous logistics and long delays between shipments. It supports a mission. It does not sustain a settlement. The difference matters. So food must be grown, not in open fields, but within controlled environments that replace every condition Mars cannot provide. A greenhouse on Mars is not a structure with glass walls. It is a sealed, pressurized system where temperature, humidity, and atmospheric composition are regulated constantly. Plants grow in hydroponic or aeroponic systems, meaning they receive nutrients through water or mist instead of soil. Light does not come from the sun alone. It is supplemented or replaced by arrays of light-emitting diodes operating for up to 16 hours each day to maintain growth cycles. This demands energy, continuous, reliable energy. The cost of running such systems at scale is significant, especially when power availability fluctuates. Every plant becomes part of a larger equation balancing light, water, and electrical input. But even with controlled systems, the surface itself offers potential. Martian regolith contains many of the mineral nutrients plants require. Yet it also contains perchlorates, chemical compounds that interfere with biological processes. Before any crop can grow in this material, those compounds must be removed, either through washing or biological treatment using bacteria that break them down. This adds another layer of processing. Some crops have shown promise under simulated conditions. Potatoes, sweet potatoes, lettuce, radishes, kale, and certain legumes have all been grown in controlled environments designed to mimic aspects of Mars. But these experiments have not occurred under actual Martian gravity or radiation. The results are encouraging, not definitive. Food also carries psychological weight. Across every long-duration mission studied, the quality and variety of meals consistently rank among the most important factors affecting morale. A limited menu, repeated over months, leads to reduced intake, declining health, and strain within the crew. Eating becomes routine, then obligation. But a fully closed system introduces its own challenges. Nutrients must cycle continuously. Human waste is processed back into growing medium. Plant matter is recycled. Pest control must function within a sealed environment. Nothing can be discarded. Everything must be reused. And if the system falls short, even slightly, the effects accumulate. A 10% deficit in caloric production leads to gradual weight loss. Over time, this becomes malnutrition, weakening the immune system and impairing cognitive function. It does not announce itself suddenly. It builds, quietly, until it cannot be ignored. A diagnosis begins without a corridor to send you down. There is no ambulance, no operating theater beyond what you carry, and no specialist arriving through a door. Care exists within the habitat, bounded by what the crew can do with what they have. One member is trained as a flight surgeon or medical officer, but that role replaces an entire system. Across isolated environments on Earth, certain emergencies appear with steady regularity. Appendicitis, kidney stones, dental fractures, bone breaks, and cardiac events have all occurred in Antarctic stations and on submarines. The difference there is distance measured in hours or days. Here, distance is measured in months. But consider appendicitis. The appendix becomes inflamed and risks rupture, which can lead to infection throughout the abdomen. The standard treatment is surgical removal. On Mars, that operation must happen inside the habitat, using pre-packaged instruments, with the crew assisting one another. Sterility must be maintained. Monitoring must be continuous. And there is no second opinion in the room. Communication does not solve this gap. Advice can be requested from Earth, but messages travel with delay. By the time a surgeon receives information, evaluates it, and responds, 44 minutes have passed between observation and guidance. In surgery, complications develop in seconds. Decisions cannot wait for distant confirmation. Studies have tried to quantify this risk. In 2019, modeling of medical scenarios for Mars missions suggested that without real-time specialist support, the probability of a serious emergency becoming fatal increases by a factor of 3 to 5. The margin for error narrows. Medication introduces another limit. Pharmaceuticals degrade over time. A mission lasting 3 to 5 years must account for shelf life, storage conditions, and the possibility that some drugs will expire before they are needed. Resupply follows orbital constraints, arriving only at specific intervals. Manufacturing medicine locally would require chemical synthesis systems that have not been demonstrated in space. But not all conditions are acute. Some persist, Dental emergencies, for example, are among the most common issues in isolated missions. A cracked molar can produce continuous pain, affecting sleep, concentration, and overall function. Without a dentist, treatment becomes management, often lasting weeks. Radiation exposure adds a longer arc of risk. It increases the likelihood of cancer, contributes to neurological changes, and may weaken immune response. These effects do not appear immediately. They accumulate, interacting with other stresses to create conditions that evolve over time. And so, medical planning extends beyond individual cases. Protocols must be written in advance for scenarios that may or may not occur. The crew must be prepared to treat conditions they cannot fully predict, using tools that cannot be replaced once consumed or damaged. But there is a quieter reality beneath all of this. The crew may outlast some of their equipment. They may reach a point where certain treatments are no longer available. And in some cases, they may face outcomes that cannot be altered, only managed within the limits of what remains. Before you open the airlock, you become the boundary. Everything that keeps you alive is no longer built around you. It is worn. A Mars suit is not a tool you carry. It is a small spacecraft shaped to your body, maintaining pressure, temperature, oxygen, and waste removal in a place that provides none of those things. If it fails, there is no delay between malfunction and consequence. The suits we use today were not built for this. The extravehicular mobility unit, developed for use on the International Space Station, weighs about 130 kilograms and is designed for microgravity. It functions in an environment where walking is unnecessary, where joints do not carry weight, and where the body floats rather than presses against the ground. On Mars, that design cannot translate directly. Movement requires articulation. Balance matters. Load returns. But a new generation is in development. The Exploration Extravehicular Mobility Unit, known as XEMU, is intended for planetary surfaces. It introduces joints that allow bending at the hips, knees, and ankles, enabling walking, crouching, and kneeling. The goal is mobility that approaches natural movement. Yet the system remains unfinished, with engineering challenges still unresolved and performance in a Martian environment unproven. Mars introduces requirements beyond current designs. The soil carries chemical compounds that can degrade materials, so seals must resist perchlorates over long durations. Dust accumulates through electrostatic charge, clinging to visors and joints, so mitigation systems must reduce buildup without constant maintenance. Operational lifespan extends from weeks to years, meaning components must endure repeated use without replacement. But degradation is not always visible. The fine dust particles that cover the surface are angular, formed without water erosion, and they act as abrasives. Over time, they wear down the soft interfaces where the suit connects at the helmet, gloves, and boots. A seal does not fail suddenly. It weakens. It allows a slow loss of pressure. In an environment where external pressure is near vacuum, even a gradual leak becomes critical. Time outside is limited. Radiation exposure accumulates with each excursion, adding to the total dose the body carries. Every minute spent on the surface contributes to long-term risk. But remaining inside carries its own constraints. The crew must balance these competing demands, choosing when to go out, how long to stay, and what each moment costs. And before each excursion, the suit becomes part of you. Layers are checked, connections sealed, systems verified. You carry your atmosphere with you, contained within a structure only millimeters thick at its most critical points. The distance between function and failure is measured in material, not space. Then the airlock opens. The surface receives the first imprint of your presence, a footprint pressed into dust that has remained undisturbed for billions of years. You stand there, enclosed, supported entirely by a system you cannot repair in real time, on a world that offers no response to your arrival and no accommodation for your survival. There are moments when distance is not measured in time, but in absence. During solar conjunction, Mars passes behind the Sun relative to Earth, placing the star directly between both planets. The Sun's outer atmosphere, called the corona, fills that line of sight with charged particles that scatter radio signals. Communication does not slow, it stops. This alignment occurs roughly every 26 months. It is predictable, calculated years in advance, yet its impact remains absolute. For about 2 weeks, no message travels between Mars and Earth. On either side of that period, signals degrade, becoming unreliable before fading entirely. The connection narrows, weakens, then disappears. But the mission does not pause. Systems continue. Decisions continue. The crew must operate without any external input, handling every task as if they are the only authority available. Guidance from Earth is not delayed. It is absent. Every procedure, every response, must come from within the habitat itself. We have seen a smaller version of this. In 2021, during a conjunction period, the Perseverance rover was placed into a pre-programmed state. Commands were uploaded in advance, and then the mission entered radio silence. Engineers on Earth described the experience as unsettling, even though no human life depended on the outcome. The absence of feedback changed the perception of control. But for a crew, this is not an isolated event. It is part of the mission timeline, repeating at regular intervals. Each conjunction becomes a period where the crew functions entirely on its own, not as an exception, but as an expected condition. Preparation must account for it from the beginning. This changes how training is approached. On the International Space Station, Mission Control provides continuous support, monitoring systems, assisting with procedures, and responding to anomalies. On Mars, that structure cannot exist. The crew must assume those responsibilities permanently. They do not rely on Earth as a backup. They replace it. Medical scenarios become more complex under this constraint. A condition that would normally involve consultation must be handled without it. Diagnosis, treatment, and follow-up occur without external confirmation. The uncertainty increases, not because knowledge is absent, but because validation is delayed beyond usefulness. But the effect is not only operational. During conjunction, Earth is no longer part of the crew's immediate experience. It is not visible through communication. It does not respond. For 2 weeks, the connection that defines distance becomes indistinguishable from absence. And when the alignment ends, communication returns all at once. Messages arrive in sequence, carrying updates that have accumulated over days. News, conversations, and personal events reappear without transition. The time that passed separately reconnects abruptly, compressing what was distant into a single moment of reception. A checklist includes it, quietly, among systems and contingencies, not as a possibility, but as an outcome that must be planned. In a multi-year mission with a small crew, operating under layered risks, the probability is not abstract. Someone will die. The question is not whether, it is what follows. There is no infrastructure for this moment, no mortuary, no ceremony prepared beyond what the crew can create, and no community beyond those who remain. The body cannot be returned. The distance does not allow it. Decisions must be made within the habitat, using procedures defined before departure. One option is burial in the regolith. It is the simplest in concept, placing the body into the surrounding soil. But the ground carries perchlorates, chemical compounds that introduce contamination risk. A burial site may also lie near future habitation zones or resource extraction areas, creating long-term complications for both health and operations. Location becomes a constraint, even in death. Another approach is containment. Some mission plans include sealed storage units, designed to isolate remains either within the habitat or in a dedicated external structure. This preserves the environment and avoids contamination, but it introduces a different weight. Living alongside a sealed compartment that holds a colleague changes the internal space in ways that are difficult to measure and have not been fully studied. But beyond physical handling, there is a legal absence. No international framework governs death on another planet. There is no jurisdiction to assign authority, no established process for investigation, no formal system for certification. The crew must document what occurred, recording observations, times, and conditions. That record becomes the only account until it can be reviewed later, reconstructed by agencies on Earth from incomplete data. Grief unfolds within the same confined system that must continue functioning. In every long-duration mission studied, the loss of a crew member affects performance, decision-making, and cohesion over extended periods. The response is not contained to a moment. It spreads through daily routines, altering interactions and focus. But the mission does not pause. There is no immediate return option. Launch windows define movement, not circumstance. Even in the presence of loss, operations continue because they must. Systems require attention. Survival depends on continuity. This places the crew within a lineage that extends beyond this mission. Expeditions across polar regions, early ascents of Everest, and previous space missions have all carried the same condition, that not everyone returns. Each instance shaped decisions that followed, influencing how risk is accepted and understood. And on Mars, the outcome remains. A marker placed in the soil, identifying a person who traveled farther than any before, now part of the environment they entered. Over time, dust will settle. Winds will move it. The surface will shift, but the presence remains, recorded in a place that cannot be revisited easily, defined by a distance that does not close. The first cry will sound inside a sealed structure, not under an open sky. It will mark a transition that has never occurred before, not in any recorded history of life on Earth. A human born on Mars would represent the first time our species begins development under a different gravitational constant from the very beginning. But we have no direct model for what follows. No mammal has ever been conceived, carried, and born outside Earth's gravity. Research conducted in space has focused on microgravity, where conditions approach weightlessness, not the partial gravity found on Mars. The difference matters. 38% gravity still exerts force. It still shapes growth, but it does so in ways we have not observed. Experiments with rat embryos in microgravity provide only limited insight. These studies have shown abnormalities in spinal development, changes in inner ear formation, shifts in organ positioning, and altered immune responses. Yet these results come from an environment without gravity, not reduced gravity. They cannot be directly applied to Mars. They only suggest that development is sensitive to the forces surrounding it. On Mars, every stage of growth would occur under a different baseline. A developing skeleton would form under lower compressive load, affecting bone density and structure. The cardiovascular system would establish circulation patterns suited to reduced gravitational resistance. Neural development, including balance and spatial awareness, would adapt to a world where orientation is defined differently. The result would not be a weakened version of a human body. It would be a body optimized for a different environment. Based on current understanding, certain traits can be anticipated. Greater height may emerge due to reduced compression along the spine during growth. Bone density would likely stabilize at lower levels, sufficient for Mars but not for Earth. The heart would operate with lower baseline output, reflecting reduced demand. The inner ear, responsible for balance, would calibrate itself to a different gravitational signal. But another factor operates continuously. Radiation levels on Mars exceed those considered safe for children on Earth. Exposure begins before birth and continues throughout development. The long-term effects remain unknown. There is no existing literature describing how a growing human body responds to this combination of reduced gravity and elevated radiation. And beyond biology, identity begins to diverge. A child born on Mars would not have experienced Earth directly. They would not have felt its gravity, breathed its atmosphere, or seen its unfiltered sky. Their understanding of Earth would come through description, images, and delayed communication. It becomes a place that exists, but not one that has been lived. Over generations, these differences accumulate. Evolutionary biology suggests that consistent environmental pressure can produce measurable changes within 10 to 20 generations, roughly 300 to 600 years. On Mars, those pressures are constant and distinct. So the first human born there does not represent an extension of Earth. They represent the beginning of a separate trajectory. Not a visitor, not a temporary inhabitant, but the first individual shaped entirely by a world that operates under different rules, moving forward into a future that has no direct precedent. Imagine beginning not with a landing, but with a horizon altered slowly, almost imperceptibly, until the sky itself changes character. The long ambition behind every mission extends beyond survival. It reaches toward transformation, the idea that a world once hostile could be reshaped into one where you stand without protection. To approach that, several conditions must shift together. The average surface temperature would need to rise by roughly 60 degrees Celsius. The atmosphere must thicken to at least 1/10 of Earth's sea level pressure. Oxygen must accumulate in sufficient concentration to support human respiration without mechanical aid. Each requirement is linked, and none can occur in isolation. But the proposed methods reveal the scale of the challenge. One concept involves orbital mirrors, vast reflective structures positioned around the planet to redirect sunlight toward the polar regions. By warming the carbon dioxide ice stored there, the gas would sublimate, meaning it would change directly from solid to gas, thickening the atmosphere. The mirrors required would span hundreds of kilometers, far beyond any structure humanity has built or assembled in space. Another approach considers super greenhouse gases, engineered compounds designed to trap heat far more effectively than carbon dioxide. These molecules, often fluorine-based, could raise planetary temperatures if released in sufficient quantity. Yet producing them at the scale needed would require industrial capacity greater than anything currently operating on Earth, then transporting or manufacturing it entirely on Mars. A more forceful idea involves redirecting ammonia-rich asteroids from the outer solar system. Their impacts would release nitrogen and water vapor, contributing to atmospheric pressure and potential warming. Each collision would deliver energy comparable to thousands of nuclear detonations. The process would reshape the surface while attempting to build an environment. But all three paths encounter the same constraint. Mars has lower gravity and no global magnetic field. Gravity determines how strongly a planet holds its atmosphere. A magnetic field deflects charged particles from the sun, known as the solar wind, which would otherwise strip gases away. Without that protection, any atmosphere created would gradually erode over time, repeating the same loss that occurred billions of years earlier. A proposed solution places a magnetic shield at the Mars L1 Lagrange point, a region where gravitational forces balance, allowing a satellite to remain fixed between Mars and the Sunday. This system would generate an artificial magnetic field large enough to deflect incoming solar particles. It remains theoretical. No comparable structure has ever been built. Even under optimistic assumptions, the timeline stretches far beyond individual lifetimes. Initial warming and atmospheric thickening might take hundreds to thousands of years. Achieving breathable conditions could require tens of thousands more. But within that span lies a deeper question. If life exists beneath the surface, adapted to present conditions, altering the planet would erase that environment entirely. The act of making Mars more familiar to us may remove whatever belongs to it now, leaving a transformed world shaped by human intention and defined by what was lost in the process. Consider a checklist that cannot be shortened, only completed, each item representing not refinement but invention. The mission described so far depends on systems that do not yet exist, in a form that can survive the environment you are entering. What remains is not engineering margin, but absence. Closed-loop life support stands first, because everything else depends on it. A closed-loop system means air, water, and waste are continuously recycled with minimal loss, forming a self-contained cycle. On the International Space Station, this loop is partial. Filters clog, components degrade, and resupply missions deliver replacements every few months. A Mars system must run for years without those shipments, with limited spare parts and no external technicians. Such a system has never operated at that scale or duration. But radiation remains unresolved at a more fundamental level. Galactic cosmic rays, high-energy particles moving near the speed of light, pass through conventional shielding with limited attenuation, meaning reduction rather than complete blocking. No material currently known can fully stop them without impractical mass. Pharmaceutical countermeasures, drugs intended to protect tissue from damage, remain experimental and incomplete, particularly for the brain. Food systems follow the same pattern. A fully closed agricultural loop must recycle nutrients from waste, sustain plant growth indefinitely, and maintain caloric output without external input. Experiments such as Biosphere 2 demonstrated partial success, but required intervention and experienced imbalance within months. No system has maintained stable human nutrition autonomously for years. The ascent vehicle problem persists in parallel. Launching from Mars requires lifting tens of tons into orbit, yet the largest mass ever landed there is about 1 ton. Entry, descent, landing, and ascent at that scale have not been demonstrated even once. The gap is not incremental, it is categorical. Medical autonomy introduces another layer. An autonomous surgical system would combine robotics, imaging, and decision support, allowing a crew member to perform complex procedures without real-time guidance. Current robotic surgery depends on continuous expert control. Removing that link transforms assistance into independence, and that transition has not been completed. Power systems extend the same uncertainty. Small fission reactors have been tested, but scaling them to support habitation, manufacturing, and agriculture simultaneously has not occurred in any off-Earth environment. Reliability over multiple years without servicing remains unproven. But the most subtle gap is psychological. No validated framework exists for sustaining mental stability under permanent separation, delayed communication, confined living, and cumulative risk. Studies provide fragments, not solutions. The honest assessment follows from this list. The timeline is not set by launch schedules or funding cycles. It is defined by the slowest unresolved problem, and several problems here do not yet have a clear path toward resolution. A list of names, longer than expected, arrives from places that have never shared a common horizon. In 2012, a private initiative opened applications for a one-way journey, and within 2 years, more than 200,000 people had volunteered. They came from every continent, every profession, every stage of life, each offering themselves for a destination defined by distance and finality. Selection, when it occurs within established agencies, follows a narrower path. Psychological screening prioritizes emotional stability, meaning the capacity to remain consistent under stress without sharp swings in behavior. Adaptability follows, the ability to adjust routines and expectations when conditions change without warning. Conflict resolution becomes essential in confined groups, where disagreement cannot be escaped, only managed. Tolerance for ambiguity is measured as well, describing comfort with incomplete information and delayed answers. Curiously, low novelty seeking is preferred because those who constantly crave new stimulation tend to deteriorate when every day becomes structurally identical. But the mission described here introduces a criterion that remains largely unspoken. The ability to process permanent loss becomes central. To leave Earth in this context is not a long absence, but a conclusion. You would need to absorb the absence of familiar places, the voices that shaped your life, the future you once assumed would unfold differently, and continue functioning with clarity and purpose. Some have argued that framing matters. A figure who walked on the moon has suggested that such travelers should be understood as colonists, not as people sent away. The distinction is subtle but important. A colonist carries intention, a sense of building rather than abandoning. Another voice, an engineer who has spent decades advocating for human settlement beyond Earth, proposes that certainty may be easier to endure than uncertainty. Planning for a return that may never come creates a tension between hope and doubt, while a one-way commitment removes that oscillation. History offers a quieter parallel. Long before instruments could guide them, navigators crossed vast oceans in vessels built from wood and fiber, guided by stars, currents, and memory. Some never reached land. Those who did established cultures that persist today. None returned to where they began, because the journey itself defined a new origin. But personality research refines this image further. Studies of individuals in Antarctic stations, submerged vessels, and orbital habitats show that success is less about fearlessness and more about purpose. Purpose, in this context, means a sustained sense that the work being done justifies the cost of doing it. It allows discomfort to be integrated rather than resisted, and isolation to be interpreted as part of a larger pattern rather than a void. So we arrive at a quieter question. What kind of person chooses this path, knowing its terms are fixed and irreversible? And what does it reveal about us that such people exist, that they step forward in large numbers, and that we consider seriously and repeatedly, allowing them to go? At the end of a long shift, when instruments fall quiet and the habitat settles into its steady rhythm, you step outside and look upward, not searching for constellations, but for a single point that carries an entire history. It is there, but not as you remember. From the surface of Mars, Earth appears as a magnitude 1.8 star, bright enough to notice, yet indistinguishable in size from any other fixed light. It does not resolve into oceans or clouds. It does not suggest continents or weather. It is simply present, a steady brightness among many others. With a small telescope, the illusion changes slightly. Earth becomes a tiny blue-white disk, and nearby, separated by a narrow gap, the moon appears as its own point of light. Together they resemble a binary system, two objects bound together, distant and complete. You can see them, but you cannot approach them. But this is the first time in human experience that home has been reduced to that scale. For every observer before, Earth filled the sky or the horizon. It was something you stood on, something that surrounded you. Here, it becomes something you observe from outside, rising and setting with the rotation of another world. There is a known shift that occurs when people see Earth from orbit, often called the overview effect, a cognitive reframing where boundaries dissolve and the planet is understood as a single fragile system. That experience is usually brief, a moment framed by return. On Mars, it becomes continuous. Each clear night repeats the same recognition, without interruption, without closure. Communication persists, but altered. Messages travel across space with a delay that prevents immediate exchange. A conversation becomes a sequence of recorded thoughts. You send a sentence and wait. A reply arrives later, shaped by a moment that has already passed. Time separates even the act of speaking. The connection becomes abstract. People you know continue their lives, their voices transmitted as data, their presence reduced to signals. Events unfold without you, and your awareness of them arrives delayed, incomplete. The distance is not only physical, it is temporal. But there are intervals when even that thread disappears. During solar conjunction, when the sun stands between the two planets, communication halts entirely. The radio link is disrupted by charged particles, and for a period of roughly 2 weeks, there is no exchange at all. At the same time, Earth itself is hidden from view, lost in the glare. For those days, the point of light is gone. There is no visible marker of origin, no incoming voice, no confirmation beyond memory. The concept of home remains, but it is no longer reinforced by sight or sound. When conjunction ends, the star returns. Messages resume. The connection is restored, but altered by absence. Over time, repetition changes perception. The light rises each night, follows a path, and sets again. You learn its timing, you anticipate its appearance. And gradually, it becomes part of the background, one object among many, known in meaning but ordinary in presence. At some point, without a clear moment of transition, the star that contains everything familiar is no longer something you look toward with urgency. It is simply part of the sky. A threshold is crossed without ceremony, not marked by a flag or a declaration, but by accumulation, by a point at which leaving becomes harder than staying. The first crew does not represent permanence. They are an outpost, a temporary extension that can still be withdrawn if conditions demand it. But that status does not last. Population becomes the first constraint that quietly reshapes intention. A small group can survive, but it cannot sustain genetic health across generations. Studies in population genetics suggest that fewer than roughly 160 individuals introduces significant risk of inbreeding depression, meaning reduced health and fertility over time due to limited genetic diversity. To avoid that outcome, either the initial population must grow rapidly or a continuous exchange of genetic material with Earth must be maintained, but logistics begins to pull in the opposite direction. Every shipment across interplanetary space carries cost, delay, and uncertainty. As infrastructure expands, habitats deepen, and systems interconnect, the investment accumulates into something that resists abandonment. At a certain point, dismantling the settlement requires more effort than sustaining it. That moment is not fixed in advance, but planners assume it exists and design toward reaching it deliberately. Supply chains evolve in stages. Early missions depend entirely on Earth, with every kilogram calculated and delivered across months. Later systems begin to produce oxygen, water, and some portion of food locally. The decisive shift occurs when the settlement can endure an entire orbital cycle, roughly 26 months, without any external resupply. At that point, continuity is internal, not imported. Communication follows a similar transformation. Initially, every update, every decision, every narrative originates from Earth. Over time, internal networks develop. Local events are recorded, shared, and interpreted within the settlement itself. When the flow of information within Mars exceeds the flow arriving from Earth, a subtle change occurs. The primary context for understanding life is no longer external, but governance introduces tension. Authority may begin with agencies that funded and planned the mission, supported by frameworks written before departure, yet operational reality will differ from those assumptions. Decisions made under distant oversight may conflict with immediate conditions on the ground. The first serious disagreement between Earth-based control and local necessity will shape the political structure that follows. Economic relationships add another layer. Initially, the settlement consumes resources without return. If it begins to produce something valued beyond its surface, whether material, knowledge, or innovation, it shifts from dependency to exchange. That transition alters the balance between the two worlds, redefining influence and autonomy. Then comes the demographic turning point. When births on Mars exceed arrivals from Earth, the majority of the population consists of individuals who did not choose to leave. Their reference point is not departure but origin. Earth becomes a place described rather than remembered. But irreversibility is not declared in a single event. It emerges through these converging changes: biological, logistical, informational, and cultural. Each one reduces the feasibility of reversal. Each one strengthens the continuity of presence. And at some unmarked moment, the idea of leaving ceases to be a plan at all. It becomes a story about a past that no longer defines the present, on a world that now continues on its own. A child takes a first step under a sky that has never carried rain, and without any announcement, a process begins that will not reverse. Divergence does not arrive as a sudden change. It accumulates quietly, generation after generation, shaped by conditions that differ in small but persistent ways. From the beginning, the environment alters development. Gravity on Mars is lower, and that difference influences how bones form, how muscles distribute load, and how the cardiovascular system circulates blood. Over time, bodies calibrate to that constant. Radiation adds another influence, increasing the rate at which DNA changes occur. Diet shifts as well, constrained by controlled agriculture, altering nutrient intake and metabolic patterns. Each factor alone is manageable. Together, they begin to separate one population from another. But the most fundamental mechanism is isolation. In evolutionary biology, reproductive isolation describes a condition where two populations no longer exchange genes. Initially, this separation is logistical. Distance, time, and cost prevent regular interaction. Over longer periods, Isolation can become biological as accumulated differences reduce compatibility. This process defines speciation, the formation of distinct species from a common origin. Within the body, another layer of divergence unfolds. The human microbiome, the community of microorganisms living within and on us, numbers in the tens of trillions and plays a central role in digestion, immunity, and even mood regulation. On Mars, this microbial ecosystem would be shaped by a limited environment, controlled inputs, and reduced exposure to the diversity found on Earth. Within a single generation, that internal landscape would begin to drift. Radiation continues to act as a constant background force. Higher exposure increases mutation rates, meaning genetic variations appear more frequently. Over time, traits that offer resilience, whether in cellular repair or tissue protection, become more common through natural selection. The genome begins to reflect the conditions in which it persists. But divergence is not only biological. Psychology adapts to context as well. A population raised within enclosed habitats, under artificial cycles of light, without oceans, forests, or open air, develops expectations and perceptions shaped by those boundaries. Concepts tied to vast natural spaces may lose relevance, replaced by an understanding of environment as something constructed and maintained. Language follows a similar path. Isolated groups modify speech through use, creating new terms, shifting meanings, and developing expressions unique to their experience. Over decades, differences accumulate. Over centuries, dialects may separate into distinct forms, each reflecting the environment and culture in which it evolved. The question that emerges is not easily resolved. At what point does a population become something new? Biological definitions rely on reproductive isolation, but identity extends beyond genetics. Culture, memory, and shared understanding all contribute to how we define ourselves. But as generations pass, the connection to Earth becomes more distant, not only in space, but in experience. The people born under that sky carry a lineage that began elsewhere, yet unfolds entirely in a different context. Over time, the distinction becomes less about departure and more about origin, as a new branch of humanity continues along its own path. We shift our gaze outward and then back again, not to compare landscapes, but to understand a contrast written into planetary history. The journey toward Mars is also a study of what remains behind, a way of seeing Earth not as default, but as outcome. The evidence begins with atmosphere. Mars preserves a record of loss, a sequence where protective systems failed and the surface transformed. A magnetic field, generated by motion in a planet's molten core, once deflected charged particles from the sunday. When that field weakened, the solar wind interacted directly with the upper atmosphere, gradually stripping it away. Over roughly 500 million years, pressure fell, water destabilized, and conditions for surface life disappeared. But that timeline also frames Earth differently. Our planet retains a magnetic field, sustained by internal heat and rotation, maintaining a barrier that shapes everything above it. Yet this protection is not permanent. Stellar evolution predicts that the sun will slowly increase in brightness, altering temperature and atmospheric chemistry on a timescale of about 1 billion years. The systems that support life are stable now, but they are not fixed. The more immediate lesson is structural rather than distant. Mars shows how sensitive planetary balance can be. Magnetic shielding, atmospheric thickness, and liquid water exist in a coupled system. When one component shifts beyond a threshold, the others follow. The transition is not evenly gradual. It accelerates, moving from habitable conditions to a stable but sterile equilibrium that persists for billions of years. Water illustrates this contrast with particular clarity. Mars still contains large quantities of it, stored in polar ice, trapped in permafrost, and possibly present as briny liquid beneath the surface. Yet, without sufficient pressure and temperature, that water cannot exist freely on the surface. It remains locked, inaccessible to organisms that depend on liquid stability. Presence alone is not enough. Conditions define usability. But the act of preparing for Mars has already reshaped activity on Earth. Research into isolation, confinement, and delayed communication has produced protocols now applied in environments far removed from space. Antarctic stations, offshore platforms, and submarine crews operate using methods refined through planetary mission simulations. Knowledge generated for one context extends into others, linking distant preparation with present application. At a broader scale, planning to leave Earth alters perspective. The planet becomes a specific configuration rather than an assumed background. Magnetic field, atmospheric composition, hydrological cycles, and biological diversity align within narrow ranges that permit complex life. Each parameter interacts with the others, forming a system that took billions of years to develop. But the most direct lesson is visual. On Mars, the absence of these conditions is immediate. The landscape does not support unprotected presence. Air is thin, water is constrained, and radiation reaches the surface. In every direction, the consequences of imbalance are visible, not as theory, but as environment. And in that environment, Earth is reduced to a distant point of light, carrying within it a complete system that is both resilient and fragile, defined not by its permanence, but by the precise conditions that allow it to exist at all. A map ends not with a line, but with a silence, a place where there is no further path to draw. For most of human history, that silence has always been temporary. Beyond every horizon lay another shore, another valley, another city not yet seen. The world was finite, yet never fully reached. On Mars, that pattern breaks. The crew will stand on a surface that marks the limit of where a human body can go and remain alive. Beyond it lies space that cannot be crossed with return. Distance becomes final. The horizon no longer promises continuation. But ideas of home have always assumed movement. In ancient Greek thought, Nostos describes the longing to return, the narrative thread that pulls a traveler back across years and uncertainty. It is not only a destination, but a structure of meaning. A journey ends when one comes home. On Mars, that structure dissolves. There is no equivalent term for a return that cannot occur. Other traditions offer different frameworks. The concept of diaspora describes a people maintaining identity across separation from their original land. Language, ritual, and memory carry continuity even when geography is lost. A Mars settlement may attempt something similar, preserving cultural patterns from Earth while adapting them to a new environment. Yet, the scale of separation introduces a new variable. Distance is not only spatial, but temporal and experiential, reshaping what can be remembered and how it is practiced. But philosophy also turns inward. Stoic thought, as expressed by Marcus Aurelius, proposes that a good life depends not on location, but on the quality of attention given to each moment. Circumstance becomes secondary to perception and action. For someone living within a confined habitat, this approach offers a form of stability, a way to anchor meaning in daily tasks rather than distant conditions. Another perspective comes from Viktor Frankl, who argued that meaning itself is the primary driver of human endurance. His work suggests that individuals can withstand extreme environments if they perceive purpose in their experience. Applied here, survival is not only a function of systems and procedures, it is also shaped by the reasons a person holds for being there. The view outward reinforces this shift. The idea, once described as a pale blue dot, becomes literal, not metaphor. Earth appears as a distant point, small and contained, a complete world reduced to a single, visible fact. What was once abstract becomes direct observation. But this transformation extends beyond those who travel. The existence of such a mission introduces a question that applies more broadly. It is not limited to engineering or planning. It concerns choice. If you were offered a place at that distance, with the knowledge that departure is permanent, how would you weigh it? What would define the value of going? And what would define the cost of leaving? The question does not require an answer to have effect. It remains present, reshaping how we understand distance, purpose, and the meaning of a place we can no longer assume we will always return to. Records rarely begin where events begin. They begin where memory can hold them. 10,000 years from now, if Mars holds cities and generations, the first crew will exist in that narrow space between fact and origin. We will know they went. We will know what followed. Their names may thin into fragments. We have seen this pattern before. The first humans who crossed the Bering Land Bridge left no written account, no preserved voice, only evidence of movement and consequence. Everything that unfolded across the Americas traces back to that passage, yet the individuals remain largely unknown. Their significance is structural, not personal. But the Mars crew departs with a different awareness. They will have studied history, been briefed by scholars, and told with precision what their actions may initiate. They will understand that they are not only traveling, but establishing a point from which all later developments will extend. Knowledge does not prevent the act, it clarifies it. This creates a dual scale of meaning. At the level of centuries, a single life appears brief, almost negligible. At the level of origin, each decision becomes essential. Without specific individuals choosing to leave, the larger narrative never forms. The beginning depends on particular bodies, particular moments. The material consequences extend outward. Systems developed for survival in that environment, closed life support, resource extraction, autonomous medicine, are not confined to Mars. They return as knowledge, as engineering, as methods that can be applied elsewhere. A solution proven in isolation can alter conditions for populations that never leave Earth. But the biological line continues separately. Over generations, a population adapting to Mars will diverge, shaped by environment, by constraint, by accumulated change. The initial departure becomes a branching point. The species that began in East Africa extends into two trajectories, linked by origin, separated by experience. Memory within that new environment evolves as well. The first crew will live out their lives there, age within the constraints they accepted, and eventually die in a place that was once only theoretical. Their descendants will encounter these facts as inherited stories, structured narratives that explain how their society began. With time, detail softens, emphasis shifts, and the stories become foundational rather than precise. But memory does not disappear. It reorganizes. Certain images persist because they are simple enough to carry across generations. One of those images will remain constant. A small blue point in the sky, rising and setting with predictable rhythm, marking a place that is both origin and distance. For those who made the journey, that point is a former home. For those born later, it is an inherited concept, a location described rather than experienced. The meaning changes without vanishing. History, in this sense, is not only a record of events, it is a process of selection, retention, and transformation. What survives is not everything that happened, but what can be carried forward. And within that long continuity, the first crew becomes less a group of individuals and more a threshold, a moment where movement became separation, and separation became the beginning of something that continues long after the original act is complete. Fingers rest against a small circle of glass, the surface cool, the pressure light, as a planet recedes beyond reach. You can still trace continents with your eye, still separate ocean from cloud, still believe distance is temporary. The motion is slow enough to feel reversible. For a while, that moment is not symbolic. It will occur on a specific departure, at a logged time, inside a defined vehicle, following a calculated path. You will watch the curve of Earth diminish across hours, then days, until detail dissolves into brightness. The hand remains for a time, then withdraws, not because the view has ended, but because the schedule has begun. But routine replaces distance as the dominant fact. Systems require attention. Filters need inspection. Trajectories need verification. Bodies need maintenance. Each task is small and precise, yet together they sustain a fragile continuity that cannot pause. The journey becomes less about where you are going and more about what must be done now. Work becomes structure. You measure days by completed procedures, by successful checks, by the quiet confirmation that nothing has failed. There is no margin for abstraction. Survival is assembled from repeated actions, performed without spectacle, carried forward without interruption. Arrival does not resolve this pattern, it deepens it. You will assemble habitats from materials that did not choose to shelter you, circulate air that must be continuously reclaimed, manage water that cannot be replaced. The environment offers no assistance, no correction, no tolerance. Everything functions because you make it function. And the record accumulates. The first enclosure holds pressure. The first harvest sustains. The first loss is marked in a place that cannot preserve it. These are not milestones announced to an audience. They are entries in a log, necessary acknowledgments of events that cannot be undone. At night, a familiar point rises. It is small, steady, and exact. You know its composition, its distance, its history. Yet knowledge does not reduce the separation. Communication continues, delayed, structured, incomplete. The connection exists, but it does not close. But the question of meaning does not guide daily action. There is no interval to evaluate whether this is sacrifice or achievement. The distinction belongs to those who observe, who interpret from a place of safety. Here, continuity is the only requirement that matters. The hand at the glass belongs to that earlier phase, when observation still dominates experience. It is a pause, a recognition, a final moment where distance is still negotiable in perception. After that, attention turns inward, toward systems, toward others, toward the immediate conditions that define existence. Morning arrives according to a different rhythm, measured against a longer rotation, a thinner atmosphere, a light filtered through suspended dust. You wake within constructed walls, confirm that the environment remains stable, and proceed through the sequence that preserves it. This is how continuation happens, not through declarations, not through certainty, but through sustained effort applied in a place that does not support it. A decision made once becomes a practice, repeated daily, extended across time. And somewhere within that repetition, without announcement, a new normal forms, built from actions that began with a hand on glass and continued because turning away was required.